Alrighty folks, this next sequence of pre-works is going to go through the graphs of rational functions, the various components that we often find on the graphs of rational functions like vertical and horizontal asymptotes, and etc. So in this first one, I just want to introduce you to the various components of a rational function that we'll be looking at over the next several videos, and then each one will take a component and highlight it. So in this section, we're just going to look at the graphs of several of these rational functions. Here you can see this function right here, and I've given its graph. If we scroll down to the next page, you can see I've given you, again, a rational function that's a polynomial divided by a polynomial, and here's the graph of this rational function. And we're going to talk about each of the components on these graphs and make some statements. Some of this will be review, and some of it will be new content. So here again, we have this rational function, we have its graph, and we want to be able to start talking about these different rational functions. For right now, I've done a lot of the work for you, and we're just going to talk about the pieces. In later sections, you'll do the work, and you'll give the answers to the various questions. Okay, the first thing I want to point out on this graph here is I want to mention that it's actually fairly tedious for me to put my arrows on these graphs, and I know that I should, but it does take quite a bit more time in the construction of them, so I've not done that for you. Please always assume, or I guess if you ever have any questions, let me know. Okay, so let's go through the parts of this rational function here. You can see I've written it three different ways. This is the way it'll be most commonly handed to you. So we could call this expanded form. Here I've put it into factored form. And here what I've done for you is I performed the long division. And we had a pre-work a little while ago that reviewed the topic of long division. Okay? So I've got, this is how it'll usually be given, but I've already done the work to put it into factored form, and I've already performed the long division. Okay, so these are some of the things that I'm kind of interested in this graph. You can notice that this graph has a strange behavior around the domain value 3, and it also has sort of a strange behavior around the range value 5. So we'll talk about that here in just a second. Before we do that, let's go ahead and state the domain of this function. So the domain of this function is a set of values x, such that x can be any real number, except that x is not allowed to be positive 3. And we could see that here when we put the expression into factored form, that this fraction is undefined if the denominator is 3. We could also learn that from this form right here, although sometimes it's a little bit harder to see that when it's in the expanded form. Okay. Next thing we might be curious about for this graph is to find its y-intercept. How do we find the y-intercept of a graph? Well, we would just go ahead, and since 0 is in the domain, we plug 0 into the domain of this function. And if I do that, we'd have 20 times 0 minus 5. I'm going to clean that up. Divided by, I think our denominator is 4 times 0 minus 12. But that cleans up to be just negative 5 over negative 12, or 5/12. So the y-intercept for this function is the ordered pair 0, 5/12. And while this graph, it's hard to show all the components of a graph, notice our scale goes quite large for the y value, we could go label that y-intercept, and it's at the ordered pair 0, 5/12. Okay. The zeros of the function, or the x-intercepts, those aren't the same, but they are related, are wherever this crosses the x-axis. Well, to figure that out, I'm going to set the numerator of this fraction equal to 0. The numerator of this fraction was 20x minus 5 equal to 0. And if I solve this, that happens when 20x is equal to 5, or when x is equal to 1/4. So we've just found that the 0, the only 0 in this case, is 1/4, and that the x-intercept is the ordered pair 1/4, 0. So again, some of these things are harder to tell on this graph because of the scale, but I wanted to show you, I wanted to focus on the asymptotes So that's partly why that is written that way, or is zoomed out so much. But here we have the x-intercept of 1/4, 0. Okay. My thought is we should be fairly comfortable with the x and y intercepts. Even though we are doing this for a rational function, the concept of an x-intercept and y-intercept haven't changed. What is new is this notion of vertical asymptotes, and I want to look at that first. So notice in this case, this graph has an interesting behavior, and I'm going to summarize that behavior below in just a second, but many of you are probably used to already saying that this graph has a vertical asymptote at x equals 3. And if you said that, you're exactly correct, but now what I'd like to do, this is new material here, I want to discuss why we can say we have a vertical asymptote there. And here I want to say that as x approaches 3 from the right, okay, so this notation, and again this is new, x approaches a from the right is read as x approaches a coming from the right. Okay. So as I approach 3 from the right, I want you to do that on the x-axis. We're going to approach the value 3 from the right. Well, if I were to go plot those points on the graph, we would see that as we get closer and closer to 3, our y values get very big. How big? Arbitrarily big. So we'll say the r of x values, the y values, approach infinity. Okay? So this is new material here, folks. I want to be able to, with arrows, sort of describe what's happening with this graph. So here's the domain axis, and look at these arrows I drew. I drew a value here, and a value here, and a value here. And what are these arrows doing? The arrows are approaching 3, but they're specifically coming from the right. And I plotted corresponding points on the graph, and what are these y coordinates doing? They're getting larger and larger. And so we summarize that behavior this way. As x approaches 3, but coming from the right, the range values, or the y values, of r of x are approaching infinity. Similarly, as x approaches 3 from the left, so that's as we approach 3 from the left, the y values are going to be doing what? Well, let's find out. So as I approach 3, but I come from the left, my y values are becoming very, very negative. So we'd say r of x equals minus infinity. Folks, this is new material, so I know this might feel a little bit confusing at this point. Okay. So I think that you're used to saying that this graph has a vertical asymptote at x equals 3. But it's actually this behavior down below here that actually explains why there's a vertical asymptote there. I know you're used to saying, well, I drew a dashed line, and so the equation of the vertical asymptote is just the equation of that dashed line. And that is still true in principle, but we want to be using this behavior notation going forward. And if this is feeling confusing, this is just beginning to scratch the surface of what you'll do with these in calculus. Okay, so I want to give you some exposure to this arrow notation, as I call it. Okay. The next thing is that this graph has a horizontal asymptote, where it has a horizontal asymptote at y equals 0. If you go look, we see this dashed line that I've drawn for you. Sure, folks, I said at y equals 0. That's a mistake. It should be at y equals 5. Excuse me. So we have this horizontal asymptote at y equals 5, and notice what we see. Okay. As the graph goes far to the right, so if I take this x-coordinate right here, that gives me this y value, and if I take this x-coordinate right here, this gives me this x value, and as I take this x value, it gives me this y value. So what we see is that as x approaches positive infinity, this means goes far to the right, the y values of this function were approaching 5. So this is that arrow notation that we're just beginning to get a glimpse of. I picked this x coordinate, that gave me this y value. Notice that this y value is kind of close to 5. And if I took a x coordinate even further to the right, I got a y coordinate that was even closer to 5. And the further I go to the right, the closer my y values on the graph of this function get to 5. Okay. Similarly, as x does what? So to find the long-term behavior, we can talk about going far to the right, or we can talk about going far to the left. So as x approaches minus infinity, that's another way for saying goes far to the left. So as the x values approach minus infinity, like this x value right here that gives me that height on the function, and this x value right here gives me that height on the function, and this x value gives me this height. The further I go to the left, as x goes far to the left, the r of x values are approaching 5. So it's this information right here that justifies this horizontal asymptote. So again, this is new. We're using this arrow notation to begin to help to justify these asymptotes. Okay? In this case, the oblique asymptote or slant asymptote doesn't apply here. We'll see that in the next example. Okay? So folks, we're learning to describe this graph, and there's a lot going on. A few of these topics are old hat in that you've gotten a lot of practice with identifying the domain. I'm not saying that it's easy. It can still be tricky to identify the domain, but you've had some practice with that in the past. You know how to find a y-intercept of a function. You plug 0 in, and the y value that it spits out can then be used to construct the y-intercept. You've learned how to find the zeros and the x-intercepts. So you set the function equal to 0, which is for a fraction, it's where the numerator is 0. And we found the x-intercept, so that's the x-intercept there. If I just asked for the zeros, you would just say 1/4, but the x-intercept is that ordered pair. And I know that historically you're used to labeling, there's my my vertical asymptote at x equals 3. And here's my horizontal asymptote at y equals 5. And I know you're used to doing this just because you see these dashed lines. But what we're now doing, which is new content, is we're using this arrow notation to help us describe both the vertical asymptotes and the long-term behavior. And so we'll see this in the next video. Okay. So folks, this could feel a little overwhelming. I think that as we get through these 4 examples, it will get easier. I'll see you in the next one. Goodbye.